In order to study torsion pendulum, we must know what is torsion. Torsion means twisting of a rod or a beam when we fix one end and twist or turn another end by some external torque. Take a rod, for example, fix its lower end. I fix the lower end and now I twist its upper end by applying some torque tau. Now when I twist it through this angle theta, this theta is known as angle of twist. This theta depends upon many factors. The amount of twisting or twist angle theta depends upon number first. It depends upon the torque. When I apply torque, it gets twisted. The more I wish to twist, the more I have to apply the external torque. Okay, when I turn it by applying torque, so apply torque theta is directly proportional to tau, this twisting angle. Number second, this angle of twist depends upon the length of the rod or the beam. When it has larger lengths, it is easy to twist, but when it has shorter length, it is not easy to twist. So it depends upon the length. More the length of this wire, more easily it can be twisted. So this angle of twist depends upon the length of the rod or the beam. Length of the beam or rod. So it is proportional to L. Number third, modulus of rigidity. This twisting angle depends upon the modulus of rigidity or shear strain. G is stress, A by A stress, strain delta X by L. This is the shearing strain. Okay, stress over shearing strain. It depends upon the material we use. For example, G is 7.0 into 10 raised to power 10 Newton per metric square for iron, and G is 8.4 into 10 raised to power 10 Newton per metric square for steel. Okay, and this angle of twist is inversely proportional to G. Okay, it depends upon the torsional constant to J. Okay, this wire is a circular wire. Here J is 1 by 2 pi r raised to power 4, where r is the radius of this circular wire. If it is a beam, then J is some different value. Okay, it has some different value. Now theta is inversely proportional to this torsional constant. So twist is inversely proportional to this J. So theta is tau L G into J. These are the factors on which this torsional angle of twist depends. Okay, here we can find the torque. So torque is G J over L times theta. J is 1 by 2 pi r raised to power 4. So torque is 1 by 2 pi r raised to power 4 G over L times theta. This 1 by 2 pi r raised to power 4 G by L is constant. Let's put it some constant that is known as kappa, or just a K. It's K, just like spring constant. Okay, so kappa is 1 by 2 pi r raised to power 4 G over L. Okay, so torque here in this case is kappa times theta, and this kappa is constant for a given rod or a beam. So this is known as twisting couple. Okay, Oscillation of torsional pendulum. Okay, here I take a circular wire and hang it from a rigid support. Okay, I connect it to a circular disc at the center. Okay, so this is the disc, and if r is the radius of the disc, m is its mass, and l is the length of the wire. Okay, now suppose I hold this disc and rotate it through certain angle and give it some twist. I disturb it from equilibrium by giving some twist. I am applying torque, external torque. The more I twist it, the more I have to apply this external torque. Okay, when I release it, it starts oscillating clockwise, anti-clockwise, clockwise, anti-clockwise. So these oscillations are periodic. Take this line as a reference. Suppose this is the line, it is in equilibrium state, and now I disturb it from equilibrium through angle theta by applying some external torque. Okay, when I release, it comes back to this line. So I'm disturbing it by applying torque. So torque is proportional to theta. Torque, applied torque is proportional to twisting angle theta. So torque is directly proportional to theta, as you see here. Okay, so torque is some cons times theta. This is k, kappa. It is equal to, it is known as a torsional constant, just like a spring constant. If you take a spring and attach a mass m and it is moving back and forth, then this is the k spring constant, and the restoring force is minus k of x. Here in our case, spring constant is kappa. When I rotate it, it has what? It produces oscillation just like the spring. This is the restoring force. In our case, torque is the restoring force. So it is the restoring force. This torque is the restoring force. This must be negative. Okay. This kappa, I have already derived it in previously. It's 1 by 2 pi r raised to power 4 g by l, because the wire is circular wire and its length is l. Torque is the product of moment of inertia and angular acceleration. So moment of inertia is I, angular acceleration is alpha. It is I into theta double dot. But this as torque is minus kappa times theta. This is the restoring force developed when I give it the twist angle theta. Okay. So this torque is I theta double dot is equal to minus k theta. So theta double dot is kappa over I, k over I times theta. Okay. So this is constant. Let this constant be equal to omega square. So theta double dot is minus omega square theta. This is the second order differential equation, and acceleration here is negative times displacement. Angular acceleration negative times angular displacement. So this is simple harmonic motion. Okay. Let's calculate the time period. Time period of this oscillation, as theta double dot is minus kappa over I times theta. Theta double dot by k, this k over I is omega square, then omega is under root of k over I. Okay, or this time period will be 2 pi under root of I divided by kappa, k or kappa. Okay, now the moment of inertia of the disc at the center at the center. About an axis passing through center is 1 by 2 mr square. So I can put the value here, 1 by 2 mr square. So the time period will be 2 pi under root of 1 by 2 mr square, or this constant kappa. Okay.